In this video, I want to talk about homomorphisms. Before I define a homomorphism, let's remind ourselves what an isomorphism is. An isomorphism was a bijective function f going from G1 to G2, where G1 and G2 are both groups, where we have the property f of AB is equal to f of A, f of B. A homomorphism is going to be a weaker version of this. A homomorphism is a function that's not necessarily bijective, that has the property f of AB equal to f of A, f of B. So we still need the same identity that an isomorphism has, but we no longer require it to be bijective. It may be either injective or surjective or neither. In addition, an isomorphism is a special case of a homomorphism. It is a bijective homomorphism. A surjective homomorphism is known as an epimorphism, and an injective homomorphism is known as a monomorphism. If there's an epimorphism, so a surjective homomorphism, f going from G to H, we say that H is a homomorphic image of G. So let's look at some examples of this. For a fixed number n greater than 1, we can define a function f going from z to zn, defined by f of x equal to x mod n. This would be an example of a homomorphism. Not only that, it is also surjective. So zn is a homomorphic image of the integers. For another example of a homomorphism, if I take any two groups, G1 and G2, I can define the function f going from G1 to G2 by f of x equal to E2, where E2 is the identity of G2. So I could map every element of my first group to the identity of the second group. And this would be an example of a homomorphism that is neither surjective nor injective. One more example, let's let P be the set containing E and O, where O plus O is equal to E. This is known as the parity group of even and odd integers. The E stands for even, the O stands for odd. I want to define this function f going from the integers to P. It's going to map even integers to E and odd integers to O. And this is an example of a homomorphism. In fact, it's a surjective homomorphism. We definitely have even integers that will map to E. We definitely have odd integers that will map to O. So we have that P is a homomorphic image of Z. When we were looking at isomorphisms, we wanted to find isomorphisms because it showed us when two groups were actually the same, they were just disguised a little differently. So what about homomorphisms? What is it that we're looking at? For that, I'm going to consider this example of the parity group a little bit more. What is it that P and Z have in common? P is a much smaller group, so a lot of the properties of integers are lost. But in this case, we still have the parity of integers. We can still determine if an integer is even or odd. So as I pass from my integers to this parity group, I'm deliberately losing every aspect of the integers except their parity. Their parity alone, with its arithmetic, is preserved. So a homomorphism is looking at preserving one particular property of my set. Let's consider the group D4, the symmetries of the square. If I consider the symmetries of the square, we have two diagonals here, these two here. So every single symmetry of the square is either going to leave the diagonals the same or it's going to interchange them, since diagonals need to map to diagonals. So if I call this diagonal 1 and this diagonal 2, either 1 is going to stay the same and 2 is going to stay the same, or 1 maps to 2 and 2 maps to 1. There are two main types of elements in my group D4. Flipping along a diagonal. So if I flip along diagonal 1, You'll notice the diagonals stay exactly where they're supposed to. Diagonal 2 may flip to the other direction, but in this case, we're not considering that to be any different. And if I flip along diagonal 2, I have the same thing. Diagonal 2 stays where it was. Diagonal 1 reverses direction, but it's still in its same location. The other elements of D4 are the rotation, so Ri will consider our 0, 1, 2, 3 for depending how many times I rotate this. And we're going to let f of Ri be the permutation of the diagonals. So when I rotate, do the diagonals stay the same, exactly where they are, or do they reverse locations? Geometrically, we can see that if we rotate this square by Ri, followed by Rj, when we watch what happens to the diagonals, we see what happened to them first, and then we follow by what happens under Rj. So what this tells us is that if we perform the composition Rj composed with Ri, and then perform my function f, that's the same thing as saying f of Rj composed with f of Ri. So now we have that this is a homomorphism, and we have even more than that. Since this is surjective, S2 is a homomorphic image of D4. But S2 only has 2 elements in it. D4 is much bigger. S2 is a much smaller set. So there's very few features of my original group D4 that are preserved. But the one aspect that we have preserved here is diagonal motions. So as we pass from D4 to S2 under this homomorphism, we are deliberately losing every aspect of plane motions except for the motion of the diagonals. One of the main properties of homomorphisms, let G and H be groups, and we're going to let F going from G to H be a homomorphism. Then F of EG is equal to EH, so we map the identity in G to the identity in H. In order to prove this, let's consider F of EG times F of EG. Well, this is the same thing as F of EG using the property of a homomorphism, and the identity times the identity is the identity. Well, another property that we need here is if I have y times y is equal to y, then I can multiply both sides by y inverse to get y is equal to the identity. Referring that to up here, I have 2 things that multiply to be equal to themselves, so that thing must be equal to the identity. So the last property showed us that identity must map to identity. The next property I want to show is that inverses have to map to inverses. F of A inverse is equal to F of A inverse. For this, we have F of A times F of A inverse. Using properties of homomorphisms, this is F of AA inverse, which is F of the identity, which we just showed has to map to the identity. Well, we know that if 2 elements multiply to give me the identity, that implies that they are inverses. So F of A inverse must be equal to F of A inverse. And I have my result.